Good morning, everyone. Glad to be here. Glad to come and see Mark and other old friends here in Barcelona. I've been coming here for, 25 years or somewhere in that area, and I never get tired of coming back. I know this is a modeling conference, and I'm not going to talk very much about modeling. I'm going to talk about what goes into models and how important it is to understand the phenomenon before you begin modeling. Then modeling becomes quite easier. So we're going to talk about some new understanding that we've gained in the last 5 or 6 years about how wildfires behave. So the general goals of wildfire behavior science are to, one, improve training and education for the people who are dealing with fire, because they're the people put in dangerous situations, and they need to understand how to interpret what they see and have explanations for what they see for safety reasons. The second thing that's very important and where models are used a lot is for planning and for mitigation, because you don't have to have a fire to use a model. You can use a model to tell you the kinds of things that can happen and how to avoid those into the future. So this is where we really need improved models. Third, we need better models to improve our predictions. Normally, when people think of fire modeling, they think of fire behavior predictions of ongoing active fires. But actually, this is a very small fraction of the number of times models are used. Most of the times, models are used in planning situations, in training situations, but we do use them to support large fires and active fires. And lastly, ecological modeling. Fire is part of many different ecological processes, whether it's global climate change or whether it's just local fire effects on species habitat or on water or hydrology. Fire is part of many ecosystem models. So we need better models for that. So we have models. We have lots of models. If you're familiar, not everybody's model is up here, but if you're familiar with fire behavior modeling or fire effects modeling, there are so many systems and tools and models and maps and data that have been generated. And all of these things have been generated off of these older models that Mark's talked about, and I'll present a brief introduction to those here in a moment. These operational models, that the underlying model that relates the independent environmental factors to fire behavior, are about 50 years old at this point. Okay, and here I've just put a couple of papers up here talking about major systems in Canada, in Australia, and in the U.S. that have each these empirical models that have been designed to produce a spread rate. Fire spread rate is an important quantity. It tells us how fast fires are going to move and therefore over time how big they're going to be, and it's an important prediction for fire management. These things have been expanded to 2 dimensions, so we have fire growth simulations that can grow fires across landscapes, heterogeneous conditions in space and time. But all of these models are empirical. All of the operational models worldwide are empirical. They're either field empirical, where they're based on observations at the field scale of fires that are burning in different fuel types under different weather conditions. And the advantage of a field empirical model is you have direct applicability at the scale that you intend to use it. The problem is you have very poor control over the variables. You don't know what the wind is. You can't describe the fuels exactly everywhere. You don't control all of the factors that you can in a laboratory. In a laboratory empirical model, the good thing about it is you have excellent control over variables, but the bad thing is you have to assume that it scales to the intended scale of application, right? So if your little fires in the laboratory don't work in the field exactly the same way, then you have problems. All of these models have very well-known limitations. They don't deal with thresholds. What I mean is they can't tell us when fires will spread and when they won't spread. They tell us how fast they spread, assuming they will spread. They can't deal with discontinuous fuels or live fuel very well. Non-heading, that is not with the wind or with the up slope, non-steady winds. Many different kinds of heterogeneities these models can't deal with, and they've been known, these limitations have been known for many years. We can't use these models in systems where we want to have strong feedbacks between the fire and the atmosphere. So why in 50 years, this is a question, why in 50 years do we not have replacements for these models? Why don't we have physical, based on physics, the physics of fire spread phenomena, why don't we have physical models? Right? 50 years, certainly we've learned something in 50 years. Well, let's find out why that is. In 2009, there was this paper published. It's a review article. It reviews 19 different physical and quasi-physical models at the time, and there was lots more than that. Reviewed 19 models, and the conclusion was that identification and formulation of the processes involved in the behavior of wildland fire is problematic. That's a nice way of saying we don't know how fire spreads. Here's another conclusion from this paper published in 2003. Even though these are a little bit older, they're still perfectly valid, these conclusions, is that the science of wildfire is still in its infancy, and the physics of how fire spread is poorly understood. Numerical models are a necessary step towards wildfire prediction, and you're seeing an example of a numerical model there. But they face the enormous task of treating a physical problem where the relevant spatial scales span 6 to 7 orders of magnitude. This is a huge deal because the real physical processes are taking place on the scale of millimeters or submillimeters and subseconds. That's the scale at which heat transfer and ignition and combustion are taking place. And yet we're trying to build models based on physical principles to apply at the multi-kilometer level over hours or days. Okay? We just do not have the computational capability, even if we understood the physics, to build up from the millimeter scale to the kilometer scale. It's impossible. So these numerical models, what they do is they take shortcuts. They use very coarse cells, coarse resolution in time and space in order to get the appropriate scale that they're interested in doing it. And they still take 100 times real time to produce anything, any results. So these are the challenges we face. We don't know how fire spreads, and the scaling issue is huge. Very, very difficult. It's fairly simple to describe the overall fire spread process. It's a tightly coupled system. We have combustion and energy release. Let's see if I can find my combustion and energy release. It's not showing up there. Some of that, it generates energy, generates heat. Some of that heat is then transferred to the new fuel, which it ignites, and that starts to burn and generates more energy. So that's a cyclical system, right? Very easy to describe that. This system can also tell you, if you understand it properly, when fires can spread. If you don't get ignitions, that you do not get any more energy release and the fire stops, right? It's a very strongly coupled system. So we have a number of questions. If we're going to understand the physics of fire behavior, we have a number of questions that we have to answer. How do fuel particles ignite? I'm going to show you some surprising things here in a moment. How do they ignite? Dead particles, live particles. The thing about wildland fires is it often involves live vegetation. It's not just dead material, not just dead grass, for instance, or dead pine needles. We need to know how long do fuels burn. In an arbitrary configuration of sticks and grasses and needles and brush, how long does the fire burn there? What's its energy release rate? Live and dead, and a mixture of all those things. We still can't tell you that. Roles of radiation and convection in heat transfer. From what's burning, the heat has to go from what's burning to what is yet to ignite. How does it do that? Is it through radiation, or is it convection, or a mixture of both? Some surprising things have come out of our research recently, and we'll get into that. Only when you answer all of these different questions can you finally ask the question as to how fast fire spread. What's the effect of wind on fire spread? What's the effect of slope? Effect on fire spread, or the fire is affecting the fire itself, right? In a strongly coupled system. So these are the basic questions that have to be addressed if we hope to have reliable physical models for fire behavior. Now, there's another discipline besides wildland fire that is used all the time in buildings like this. It's called fire protection engineering, and this is a very well-developed discipline throughout the world. It's because there's a lot of money in this, right? Buildings like this are engineered to be fire resistant and to be safe for people to be in. And the thing about structure fires is they're fairly well understood. They're well understood because the materials, we can control the materials. We engineer all of the materials in the building and the configuration of it. We know it. We can describe it exactly. The other thing about it is that there are very large surfaces compared to wildland fires. The walls and furniture, very large surfaces, compared to wildland fire where we're dealing with primarily fine material. And this is a very, very critical distinction between wildland fires and structure fires. We're dealing with fine fuels, less than a millimeter in size, typically. Discrete particles separated by air. That seems like a very simple statement to make, but discrete particles separated by air means it changes how the heat must be transferred between particles, okay? And we typically have a lot of live vegetation. So this context is quite different than that context. And we can't just take these kinds of relations and apply them to wildland fire. They don't work. We've proven that. So let's ask a few simple questions and see whether our thought processes are working. How do fine fuel particles ignite? I'm talking about the little tiny grasses or fine particles here. How do particles ignite? Is it by radiation? Radiant energy is what we feel on our face when the sun is shining, right? It's transferred through the air without heating it. Is that how wildland fires spread? Well, almost all models, those 19 different models, many of these models assume that radiation is sufficient for fire spread. So we're examining this part of the cycle, right? We're going to determine how ignition happens. We can do it in a laboratory. How does the heat go from what's burning to the fuel that's left that's yet to burn? And we can duplicate that in a laboratory with an artificial heater, a propane-powered heater that produces about 40 kilowatts per square meter, which is about the same as that fire right there. So here's a question you don't have to answer, but think to yourself. Which one of these materials will ignite first in front of that heater? Okay, if we put it very, very close to that heater. Will the 1 millimeter Excelsior particles, very fine shredded wood, very dry, will it ignite first, or will that block of wood? Well, you might be surprised, but in 20 seconds, that block of wood starts to pyrolyze. You start to see smoky products coming up. In about 35 seconds, it will ignite. And after 40 seconds, you start to see some discoloration on the Excelsior, but after 5 minutes, no smoky pyrolysate, and it has not ignited. In fact, it never will ignite. It'll never ignite. It'll sit there forever and never ignite. There's some grass enjoying a nice radiant heating. If you put thermocouples on these particles to measure their temperature over time, what you see is some very interesting things. The blue line is the 1 millimeter particle, and the 12 millimeter particle is the red line. The 1 millimeter particle rises up to a temperature below 200 Celsius and just sits there. And the red particle, the red line, you can see it reaches an ignition temperature, maybe 350 degrees Celsius, and then it ignites. Well, the reason for this is that these very fine particles, they have excellent convective heat exchange. They're able to lose heat by convection to the cold air they're sitting in, as fast as they're heating up by radiation. Okay? So they're very much like cooling fins. Everybody's seen cooling fins on your lawnmower, on your CPU, and your computer. The reason that they're small fins is because that is very effective at convective cooling. Okay? They have a very thin boundary layer. I don't have time to explain all of these things, but the reason that fins work very well for cooling is that they have a very thin boundary layer, and that boundary layer is easily disturbed, and thus when it's disturbed, cold air comes in to replace the hot air next to the particle and removes that air. Okay? So if you think about yourself standing in front of a campfire, why don't you catch on fire? I don't catch on fire. You move to a distance to where the amount of heat coming in from radiation is balanced by that being lost to the environment, right? Otherwise, you'll continue to heat up and you would catch on fire. So we find a distance that's comfortable for us to stand in front of a campfire to where there's a heat balance. Heat going out is the same as the heat coming in. And these little particles can stand very, very close to the fire, much closer than large surfaces. If you think this is surprising, a lot of fire scientists are surprised by this too, because their models make the wrong assumptions. So if particles are not igniting by, the fine particles are not igniting by radiation, then it must be convection, right? It has to be, because these particles are separated by air. Remember how important that is for the wildland fire context. So it can't be conduction. It can't conduct. That's a very slow process. It can't conduct through the air. So it's got to be convection. So we can do experiments with basically hot air, flame temperature air, 600 degrees Celsius, and we can put Excelsior, that fine material, we can put that in this stream of hot air and it'll ignite in 1 second, just like you'd expect. The stick takes 17 seconds, exactly the opposite. It's opposite. Okay, so convective heating is going to be critical, just like convective cooling is. Convective heat exchange to explain fine particle ignition and thus fire spread. But we have two questions that have not been asked before by the fire science community, because everybody thought it was radiation, right? So if you think it's radiation, then you're not going to ask hard questions about how is it that convection could actually occur. Two questions. What is the mechanism of forward convection? Right? Hot air, hot flames, they want to go up. Right? And so how do they go forward? And then what keeps them down in the fuel? Because if the flames go up and they're out of the fuel, then they're not touching the fuel. So everybody's familiar with a candle flame. The reason the candle on Earth goes straight up is because of buoyancy. The temperature of that candle is 1,000 degrees Celsius. Okay? The same candle without gravity is on the right. So gravity is what pulls down on cold, dense air, which pushes up the very light, buoyant air. Okay? So flames are very hot. They're low density. They're about 1/4 the density of air that we're breathing here today. And that's why they go up. Okay? Buoyancy. So what makes them go down in the fuel? How can they stay down? And what makes them go forward? We're going to answer that right now. So we needed to do experiments in our laboratory to find out and take very good high-speed video and very careful measurements to understand how we are getting forward convection as a heat transfer process in spreading fires. So normally in laboratories, people burn pine needles, they burn Excelsior, they burn grass, but that's not very well controlled. You can't reproduce the particle properties or the bed level properties exactly every single time. So we chose a different kind of fuel. We chose laser cut cardboard. So we bought a laser cutter and we started engineering our own fuel particles in the laboratory. They look like this. We call them combs. We can make particles of any size, any dimension, any density, and we can build fuel beds exactly the same way every single time, controlling the fuel. And then we set them up in the wind tunnel. We have a wind tunnel in our facility. We have a combustion chamber. You'll see a few videos of these. So we build very tall ones, 30 centimeters tall, very short ones, sparse ones, thick ones. We have a large tilting table in the laboratory where we can populate that with these cards, these cardboard cards, and we can observe how fires are spreading and take measurements. So watch these videos. This is the kind of information I started doing these experiments. And you'll notice these little parcels, these pockets. These little pockets in the flame zone. This is a different view, moving from right to left. You'll notice these little parcels originating upstream, advecting energy downstream. But they remain identifiable. They're coherent motions in the flame zone. Right? They look like waves. This next one is fire spreading towards us. Okay, and what you'll notice there is this peak and trough structure. There's a big peak and a big U shape, right? Very persistent. And notice this billowing, very non-steady motion down here in the trough. So let's examine what's causing these behaviors, these features. I will bet that everybody in this room who's seen fire, if you were asked to draw it with a pencil on your paper, you would draw it with peaks and troughs. It looks like that, right? You wouldn't just draw a big rectangle. You draw the flames having this kind of structure because that's what we see. But before these studies, nobody knew whether those were important, whether they were just superfluous features of the flame that had no physical meaning or bearing on how fires are spreading. Okay, but we see these at every scale. We can see them in the field, right? Even in Germany. See, very regular pattern of peaks and troughs. We see them in stationary fires. This is a fire that we did out the back of our laboratory in winter. But you see the peak and trough structures, right? So it's not just a spreading fire, but even stationary fires. You see them in crown fires. This is from the Northwest Territories, the crown fire modeling experiment from the late 90s. Terry Clark examined these big U-shaped structures and described them with some thermal infrared imaging. Okay, so at every scale we see these. It turns out what's causing these is vorticity, patterns of spinning air that is induced by the flow into the fire. So what happens is you see those corkscrews, those spirals of air, and they come in pairs. And they're moving forward, and where they converge in a downward direction, they push the flames down into the fuel. Where they converge in the upward direction, they push the flames up into a peak. And this repeats across the entire front. Okay, so we're starting to see the answers to some of these questions that I posed. That why do the flames stay down in the fuel? Well, they stay down because in one place the flames are going up, and if in order for something to come up, something has to come down in order to replace that air. Okay, if you take a ball and you push it underneath a swimming pool, so where it's underneath the water, and you let it go, does it leave a hole in the water? No. Water comes in to replace that. Same way here. When hot flames are rising up, there has to be cold air coming down to replace it. You can't just have a vacuum. So the end result of this replacement of hot air by cold air turns into vorticity. And you end up having this peak and trough structure across the front where the cold air coming down is forcing the flames down into the fuels. And you can see that in some flow tracking analysis from our videos. You'll notice this trough, and notice the spinning motion on the edges of that trough. This is a video in the wind tunnel, fire spreading towards us. I want you to notice behind the front these smoke circulations. Don't look at the fire. Look at the smoke circulations behind the front. You should be able to see the plumes. It's going up in one place and then down in the other. So these circulations are going on behind the front. They're not even in the flames, but they're forcing the flames down. Let's look at that again. You can even see the smoke being pushed down through the troughs in the flame. So one of the things that we've done with this is to simply describe them. And it turns out that the wavelength, the transverse wavelength from one peak to the next, that distance, scales very well, from the laboratory all the way up to field scale. So what you're seeing on the x-axis here is the flame length in meters. On the y-axis is the wavelength. That's the distance between the peaks. And it scales all the way from our little laboratory burns in those open circles all the way up to approximately 15-meter tall flames. That's pretty interesting. And the reason that it's doing this is because the temperature of the little fires is exactly the same as the temperature of the big fires. That doesn't mean the same amount of energy is being released. It's the gas temperature is the same, and therefore the buoyancy is the same. The density of the flames is the same in little fires like a candle all the way up to the biggest crown fire. That's a remarkable fact of diffusion flames. Doesn't matter what you burn. You can burn gasoline, you can burn wood, you can burn diesel fuel or propane. The flames, as long as it's not pre-mixed with air, but is just a diffusion flame, it burns at about the same temperature. They're all about the same temperature, about 1,000 degrees. And that's the reason that you can get away with using propane burners or other artificial fuel sources in a laboratory to study fires in a relevant way. So the other thing about buoyancy is it operates on many different substances. It's not just about fire, it's about the density difference between one fluid and another. Let me show you an example of this. So what we have here is a platform with a electrically heated plate. This plate gets very hot, 400 degrees Celsius. And then we have a trough, hot water trough, upwind, where we're going to put dry ice. And you know what happens when you put dry ice into hot water? You get a water vapor, a carbon dioxide water vapor. So here's the dry ice going in. Look what happens when this water vapor that is just a flow tracer comes across and hits the copper plate. You see all the little vortices? Yeah. We would see many of the structures that we think about are particular to flame. It's just that flames are visible, and we can see them. That's why we think that they're unique. So we're getting the same patterns of vorticity off of a copper plate with much different fluids, but still due to buoyancy. And everywhere you look, when you start looking at fires, you can see all these little patterns, vortex streets traced out by the smoke. The spinning motion of the air. So let's look at what happens when we do fire on a slope. All the burns I've showed you so far are in a wind tunnel with the wind blowing. And if you look carefully here, you can see exactly the same kinds of features. You can see at the edge of the fire, it forms these peaks and their troughs. And these little parcels are formed upstream. So the scale of this, it's probably about 3 meters across the base and about 5 meters long. And here's looking down on this fire. You can see these little parcels that are forming and then moving. I want to point one other thing out here. There's a line of thermocouples right here. The line of thermocouples measuring the temperature fluctuations in the flame. Measuring the temperature fluctuations, because what you can see is the flames are very non-steady. Everybody knows that. But we're interested in the frequency. How often are those flame bursts coming forward from the flaming edge? So we can analyze that. This line of thermocouples sitting we have 64 of them. They're very, very fine wire thermocouples. They respond very, very quickly to changes in temperature. And you can see the kinds of temperature traces there over on the right-hand side. You can see that's a line of 8 thermocouples, each with a different color. And over time, what you see is this very spiky nature of the temperature fluctuations, right? Very spiky. And if you look at one of those spikes, you can follow it all the way up. So these are coherent motions in the flame, in the fluid, that are moving forward, bursting forward. Here's a close-up of some of those signals, right? You can see that In the green, the pre-ignition phase, these particles are being bathed intermittently by flame. You can see all of those spiky temperature patterns where the temperature goes up to about 1,000 degrees and then drops down to almost ambient. And then it goes back up again. And it fluctuates up and down until you get an ignition. We can analyze the frequency to try to understand what is causing that kind of a frequency. And one of the most common scaling laws that's used in engineering for scaling is called a Struhal-Froude scaling. Basically, you're producing dimensionless groups of frequency on the y-axis and a combination of wind and some length scale on the x-axis. What's interesting about this kind of scaling of frequency is that we find that the frequencies of our little laboratory fires, and that's all in those red and blue dots there, that's our laboratory fires, we have the same scaling in the laboratory for these fluctuations as we do in crown fires, in grass fires, and for stationary fires. They all fall along that same kind of a line. And the significance of that is that this is a buoyancy-driven phenomenon. It's about the density difference of the flame gases versus the surrounding atmosphere. And so this is very important because it suggests to us that our laboratory fires, as long as we're studying the right things, can be used to develop a general theory about how fires behave based on buoyancy. Okay? Very critical to establish the scaling laws and the exact physics of how things are happening. So, the final question we're going to examine here from our experiments is, what do fine fuel particles think about these flame extensions, these flame bursts, this non-steady environment? How do they ignite? How do they respond to that? So what you're seeing there is a couple of particles, a very thick piece of wood, and then a thin particle, and there are thermocouples attached to the surface of each one of those, and then one sitting out in the air. That black tube there is a radiometer to tell us how much radiation is being received by those particles. So the fire is going to be burning through this cardboard here, and then we'll have the thermocouples to record the temperature on the surface of the particle. So let's examine what we see. We see there are three colors on each one of these graphs over time. The red line is radiation. Okay, and you can see that it goes up to about 30 kilowatts per square meter. Right? The irradiance goes up to about 30. You remember one of the first slides I showed you where we had radiation from a panel at 40 kilowatts per square meter? Right? Radiation at 40 kilowatts. This only goes up to 30. And at 40 kilowatts per square meter, the fine particles could never ignite. That's just a point of reference. So the red line is radiation. The blue line is convection. That's the flame or the gas temperature, the air temperature right next to the particle. And the black line, that is the particle surface temperature. So if you zoom up to the final 20 seconds before ignition, what you see is an interesting thing, that the black line is going up in steps. It's stepping up, right? And every time it steps up, it's corresponding with a blue spike. Those are the pulses of gas, of flame gas, that are going forward, bathing those particles. And then the particle temperature in between these spikes starts to go down. It goes down in between. So here's the spike, and the particle is cooling, and then it's hit by another flame burst, and it gets a little warmer and starts cooling off, and so it steps up to ignition. It cools down even though radiation is going up. Pretty interesting. So basically, our fuel particles, these experiments have shown the fuel particles, they rise from a little bit from radiation, but they cool off by convection, just like we started talking about. The radiant fluxes here of about 30 kilowatts per square meter for just a few seconds are too low, even for large particles to ignite. And so our fuel particles in wildland fire tend to reach ignition in a stair-step kind of a fashion, dependent on flame bathing at a very high frequency. you're talking about somewhere between 2 times a second up to about 10 times a second. Depends on the size of the fire. Okay. So there are a lot of other questions. We're not going to go into all of the questions and all the investigations that we're doing on each one of these components, but we've just focused a little bit on the heat transfer and how that produces ignitions or doesn't do ignitions. So what are we going to do with this knowledge? Like I said, this isn't a modeling talk. This is talking about what do we understand about how fire behaves and how does it spread? Because if we understand it, it's going to be very easy for us to model it. Pretty much anybody could write a model once you understand the processes. What we're trying to do is develop a foundational theory of flame spread and wildfires. That still doesn't exist today. We do not have a theory about how this happens to where people in every country doing research on this can produce and contribute important contributions to that theory. We need, what we hope in the short term is that this kind of information and other material that we're developing will be incorporated into training for fire managers. And I know this is important for Mark and his firefighters, as well as our own, to help them understand what they see. When they're out on the fire line, helping them understand physically what's happening and what does it mean for safety and for any kind of actions that they're planning. Better fuel mitigation. One of the problems we have right now is we don't know how fuels are related to fire behavior. We know in general, but specifically, how are they? And if we're going to change fuels, if we're to mitigate fire behavior, how much do we have to change the fuel in order to get the required change in fire behavior? And finally, the very last one, if we understand all of these processes and have a theory about fire spread, we can have a much more reliable model. We can eliminate the variability or drastically reduce the variability contributed right now, model error, so to speak. And we still have a lot of other error, a lot of data uncertainties, but in the natural fire environment. But at least our models will have a reliable physical basis. So, thank you for your attention. I can answer any questions you might have.
Thanks, Mark. It was impressive talk. At least for the firefighter, I was following the social media going on, and some of us, we were really amazed. As you said, this is important for us firefighters because we need to understand what we see and all the physical model, well, all the models we've seen until now. They try to explain us the spread of the fire, but they didn't explain us a lot about behavior of fire. One thing that came to my mind constantly when you were talking is that we firefighters, we talk about waves of flames or rhythm of fire. Like any fire has a different rhythm. It means wave came, same, steady, steady. So that's what you have been explaining. So this brings back dignity to firefighters 100 years later. So they are not mad people. But
so science is finally catching up to firefighters?
Yeah, that's important.
That's good to know.
So thanks for doing the effort.